Hello and welcome to this IROS 2020 presentation. My name is David Paz, and today I'll be talking about autonomous vehicle benchmarking using unbiased metrics. So to start, let me start off by telling you a little bit of background and motivation for our work. I will then follow that with the approach, the set of metrics, and the notion of intervention maps that we used, as well as the data collection, the vehicles, and the various signals that we collected on a real autonomous vehicle car tested at the UCSD campus. And we'll close with the results and potential direction for future work. So just to provide a bit of context and motivation for this work, a study from 2016 has showed that an autonomous vehicle car would have to drive hundreds of millions of miles to demonstrate considerable reliability in terms of fatalities and even injuries with respect to human drivers. So this naturally leads to the question, what can we do in the meantime to keep track of the progress of self-driving cars? And this has in fact received attention from state officials like the state of California, which is now requiring any autonomous vehicle entity performing tests on public roads to have a valid permit and to also supply annual disengagement reports for their fleet. One of the biggest downsides from this engagement data that's provided by itself is that it is not sufficient to quantify long-term autonomous vehicle performance or even make quantitative comparisons, objective comparisons with respect to other autonomous vehicle systems and even human drivers. They also do not account for different types of road conditions or interactions. For example, highway driving can consist of different types of interactions compared to local city driving, where you would be interacting with a lot of pedestrians and other road users. So to account for these shortcomings, we present a number of contributions. To start, we extend the base metrics we introduced in lessons learned from deploying autonomous vehicles at UC San Diego, so that we can account for safety driver dependability. We also introduced the concept of intervention maps to capture the disengagement data with respect to a particular location and different areas. From there, we separate this data with respect to different types of road types to prevent biasing towards a particular type of scenario, such as highways or local city driving. From here, we've performed a 4-month data collection study in partnership with the UCSD Mail Delivery Center to quantify the performance of our own autonomous vehicles during an initial mail delivery run. So the base metrics that we previously introduced are relatively straightforward. They quantify the mean distance and mean time between interventions. In contrast with disengagements alone, we can capture in average how long does it take for a vehicle before the next disengagement in terms of time and distance. So this aims to address the questions of such as, do you have 5 interventions over the past 5 miles or over the past 5,000 miles? So this varies a lot and it normalizes data with respect to time and distance. But to account for safety driver dependability, we further extend this so that we can account for manual driving, but also autonomous driving. So we have these very similar types of metrics, but we separate the distance and time based on the distance and time the autonomous vehicle drove, but also the distance and time that a manual driver, in this case a safety driver, drove through. So the definitions are provided here on the right. But the concept behind this is that these metrics that are capturing autonomous vehicle data are intended to demonstrate how capable is a self-driving car of driving without any driver input. Whereas the other set of benchmarks for manual driving, in this case, mean time between interventions and mean distance between interventions, sub-M, are intended to capture how dependable is a system with respect to the safety driver. So in the ideal case, we would want the these metrics for autonomous driving to approach infinity, whereas the metrics for manual driving to approach 0. So to estimate these different metrics for both autonomous and manual driving, 2 important signals are recorded or can be recorded. So this includes vehicle pose and the enable disable signals recorded over time. So the enable disable signals can be collected from a drive-by-wire system that sets a signal to true whenever the vehicle is operating in autonomous mode, and it gets toggled to false whenever there is a manual intervention. So by analyzing these toggles, we can separate the different segments for autonomous driving and manual driving. Here, a toggle could allow us to separate the autonomous vehicle driving segments in blue, whereas manual driving will correspond to these orange regions. So a combination with this disable signals as a function of time, and the vehicle pose can provide us with the means of separating the manual driving and autonomous driving segments and compute these different values separately. Here's a brief visualization of what a vehicle pose estimation or localization algorithm could give you, where for every particular time step, we can estimate the total distance the vehicle has traveled, regardless of whether it's driving in autonomous mode or manual mode. And as soon as a toggle is executed, we can start separating the data for both manual and autonomous modes. So while these metrics provide a sense for how was the vehicle doing in terms of mean distance between interventions and mean time between interventions, there's still more information that is lacking, such as how do we incorporate the different types of road conditions into this. So this is where we introduce the notion of intervention maps to provide additional types of road conditions, and this could allow us to separate not only in terms of manual and autonomous vehicle driving, but also depending on the road conditions, such as more dynamic roads, regular roads, highway driving, etc. So these are and need to be manually defined by a human annotator to be able to define which segments are dynamic, which parts are regular. But it can also provide us with a sense of where are most of the interventions happening. So on the visualization on the left, we do have a combination of regular and dynamic roads, but we can see where the vehicle encounter most of the interventions over time. And this can actually also allow us to identify which types of interactions are the hardest. And in order to build these type of intervention maps, we propose a occupancy grid map representation where we discretize 3D space positions into a 2D cell-based grid. And so here on the left, we're looking at the algorithm that we use to associate the enable disable signals. So these are the disengagement signals, but also the position information over time. And so in the first part, we perform a disengagement to post association, where for every disengagement, we have a corresponding position, and this is over time. And finally, we populate our occupancy grid based on the toggles. So as soon as the disengagement signals drop to false, we increment the number of disengagements for that particular cell, which corresponds to a region in 3D space. So with this metrics and intervention maps in place, we performed a 4-month data collection study in collaboration with the UCSD Manley Center. We've described the design and the development of our platforms in detail in 2 previous publications. Please see the references for more details. So as President mentioned, there are a number of signals that are useful for estimating the mean time between interventions and mean distance between interventions. Here are a list of all the different signals that we collected from the vehicles, including the pose, GPS, IMU, and some of the speed and acceleration reports. But for this particular set of metrics, we only leverage pose, velocity, and disengagement reports to compute the entire metric. So the number of signals really needed for estimating these reports are relatively straightforward. So for the 2 different routes that we collected data for, one consisted of 1.0 1.9 kilometers, which was Warren College, and the other one about 1.6 kilometers, which was a 6 college mailing route. And so in terms of mean time and mean distance between interventions, on average, we can say that the vehicle drove, for at least for both different mailing routes and also for summer and fall 2019, the vehicle drove approximately 380 meters between an intervention, but also in average, it drove for about 106 seconds between an intervention. The analogy for this is also, in average, a safety driver performed a intervention for about 22.7 meters, but for approximately 12.5 seconds. So there are different types of separations of this data that we can do by separating the data into manual driving, but also in autonomous driving. So this can tell us how dependent the vehicle was during the initial run. And for a few details in regards to different types of road conditions here on, for these two different routes, the Warren College route has approximately the same distance covered in terms of trips, so about 46 kilometers for both routes. But for Warren, about 21% of the entire round trip corresponds to dynamic driving or dynamic roads, where there are some type of pedestrian interactions. There's no clear definition, road lane definitions. And for this particular route, we drove through large pedestrian walkways. So given that we have a golf cart, our vehicle is actually a golf cart, we can navigate through some of the more narrower pathways where a regular vehicle couldn't drive, but it also presents many more challenges. And these are part of the mailing route, as the mailing centers and mailing parcels are within the further parts of the campuses are within pedestrian walkways. Whereas for 6 college, more than half of this was dynamic driving due to construction areas and different types of negotiations that have to happen with construction workers. So here is a visualization of the different intervention maps that we generate for summer and fall 2019. On the left, we have this automatically generated. On the right, we have both of them combined with additional labels defined by hand. So we can see both Warren and 6 college routes. And the areas that are marked as blue correspond to regular roads, where the areas marked as black correspond to more dynamic and the types of interactions where you have construction worker interactions, but also with other pedestrians that are walking along the walkways. So as far as the different statistics for the different types of road conditions, as I mentioned, for Warren, it's over 20%, and for 6 college, it's over 50%. And we could see that in terms of dynamic and regular, the results are slightly flipped and partially the opposite, even though the total number of kilometers or total distance cover is approximately the same. We can see that there's a variation in the types of road conditions. And for this reason, it is important to separate the data depending on the different types of road conditions to prevent bias towards a particular route or particular system. It's worth noting that our vehicles were speed limited to 25 miles per hour due to one, factory settings, but also speed on the campus is also limited to 25 miles per hour. So these are interesting findings. We can, of course, separate this data and create subsets of the different benchmarks that not only cover maybe 2 different quarters that as we've shown here, but also it could cover weekly, bi-weekly, different parts of the year, different days, even at an hour interval. And with this, we hope to create a set of metrics, sort of platform that can be used for customizing different benchmarking tools geared for autonomous driving, and not only incorporate the sense of the metrics for mean time between interventions, mean distance between interventions, and even intervention maps, but also for different road categories that can also allow us to extend even further and talk about the cost of ownership, the energy consumption with respect to manual vehicles and regular human drivers. And with that, we want to encourage self-driving car entities to report continuous disengagement signals as a function of position and also various other signals. I know there's a lot to ask for, but it would bring awareness to the state of autonomous vehicle technology as it is these days, and also provide a sense of how we're doing over time. With that, thank you. I'm happy to take any questions and comments over email. Please feel free to contact me directly if you have any ideas or suggestions. I'll be happy to hear them. Thank you.